So let's talk about voltage. As a quick review, kind of for like voltage is kind of the idea of electric potential energy, right? If I have two charges and let's say they're a distance r away from each other, they're going to be exerting electrostatic forces on one another. And those electrostatic forces kind of cause them to accelerate, right? And as they accelerate, they're gonna gain kinetic energy. And the reason for that is because, if you're just isolating to the system of let's say this charge right here, right? If that's our system, yeah, this not proton, but this positive charge is gonna be doing work on this point charge. So if you want to find that work, it would be as simple as, being like, okay, so let's say it goes a distance, let's say this is RA, and then the point charge goes to a distance RB, and I want to figure out how much work was done. It would be as simple as just saying that the work done is going to equal the integral of the electric force, K Q naught little q over R squared dr, and I'm going to be integrating from RA to RB. So that would give us KQ Q over R, well, negative R, right, when you take the antiderivative, and then we would do our RB to RA for our, what do you call it, bounds, I guess? Yeah, bounds. So that would just result in us having QRA minus KQ RB. So because RA is a smaller radius, or smaller distance, sorry, this fraction will be bigger. There's positive work being done on this electron. So, and obviously, if let's say this was actually wait, I'll get to that in a second. Point is, you can show that the electric force is a conservative force, and because it's a conservative force, you can relate the work done by that conservative force being the electric force. You can relate that to a potential energy. This is going to equal negative change in U. So essentially that would be the same. So, and the reason why work is negative change in U, so if you think about gravity, right? If gravity does gravity is going to do positive work on this pen, right? So that positive work, if the pen was the only system, that's positive work. If we include Earth in the system, this is a negative change in UG, right? Starts at high, goes to low. So the UG final is less than UG initial. So that negative change in U is associated by a positive work done by FG. When you're switching systems, right? You can't have work by FG and change in U in the same system. You gotta, it's different systems. Point being, this would be the same as negative U final minus U initial, KQRA minus KQQRB, and this UF, so I guess we should distribute the negative, right? We get a form negative UF plus positive U. So the negative quantity would be the U final, and the positive U initial would be the positive term. So you could see this would fit a U initial minus U final. So the U initial would equal this quantity, KQQ over RA, which is the initial U, and then the final U is at RB. So the equation for electric potential energy is KQQ over R. So at a certain point, the electric potential energy conforms to this, right? So what is potential? Well, potential and potential energy aren't the same thing, but the idea of potential energy and potential kind of relate back to electric force and the electric field. So the electric force, as I said, it's going to equal KQQ over R squared. And the electric field is going to be given, well, I should say this. The electric force is equal to Q times E. So what this equation tells us is that, let's say this positive little q right here, right? It experiences an electric field. And that electric field is essentially creating the force. That's one way to model what's going on. Are electric fields real? I don't know. But that's one way we can model what's going on. And E is really just equal to kq over r squared. So the electric field created by this big Q over here at a distance r follows as so. And then you can find the electric force as Q times E. And if the electric field is constant, if I'm only changing this charge and I make this charge way, way, way bigger, then the force gets bigger, but the ratio between the force to the charge experiencing that force is equal to the electric field by the other charge creating the field. Hopefully that's review. Hopefully that makes sense. Whole idea being is you can get the same thing going for potential. So you could say U is going to equal KQQ over R. And this is the same thing as Q times change in V. So, sorry, oh my God, I'm not changing V. Whoa, we're not there yet. It's Q times V. So V ends up being a KQQ over R. Sorry, I'm making someone. This is just KQ over R. The big Q is creating a potential, a certain potential at Q. So, the electric potential energy is proportional to that potential as well as its charge, right? So if I increase Q, yeah, my U, the potential energy that charge experiences will go up, but the potential, I'll talk about vocabulary in a second. The potential, this is not voltage, in my opinion. I don't know. Point is, this is potential. I'll talk about what I think voltage means. And the potential stays the same because the potential is created by this charge. So over here, there's high potential, right? Because that R is bigger or smaller. And then at here, there's low potential because that R got bigger. So positive charges go from high to low potential. Now, what happens if this was an electron? Well, let's say this was an electron, or not an electron, but a negatively charged thing, right? Now, this quantity becomes negative, right? So you have negative potential energy here, and it's creating what we can call a negative potential. And now the positive starts at a certain potential, and as it gets closer, this R is getting bigger. No, it's getting smaller. What am I talking? I meant you're gonna see what I mean. The R is getting smaller, but now it's a negative quantity, and it's a scalar, right? Potential doesn't have direction. It exists on the fabric of space, and you can watch demonstrations of like potential and how it affects the space around it. It's kind of like how you take a trampoline, but gravity, that gravitational field that was bending space, potential is kind of like that. It's not really a force, it's just a quantity at a certain point that is proportional to the electric potential energy. So as R goes down, the fraction gets bigger, but it's negative. So it's still going from high to low potential. That's what protons do. Now, if I put a positive here, and this negative, if this was a negatively charged point charge, now it's going to go towards a positive, and this is still KQ over R. It's positive fraction. As R gets smaller, as R gets smaller, the whole fraction gets bigger. So electrons have been observed to go from low to high potential. What I'm going to do now is relate potential to voltage and relate that to the electric field. Voltage, in my opinion, this is how I would teach voltage to you. Voltage is a potential difference, right? there's a potential difference from this point to that point. I would call that difference a voltage. My physics teacher, he likes to call potential the same thing as voltage. That's probably fine, but and then he says things like voltage difference. But I think the way that makes sense to me is calling a specific point the potential at a specific point is just potential, and then a potential difference is voltage. Because at the end of the day, you need a potential difference to get charge moving. That's what voltage is. And in my head, when I think of voltage, I think of current. So current is moving charge, voltage causes current. That means voltage is a potential difference, right? Potential difference causes moving charge. So obviously, like if you think about, well, U final minus U initial is equal to change in U. So this is equal Q V initial. So let's say Q V final minus Q V initial. We'll call that change in U. So Q times change in V is going to equal change in U. Now let's kind of relate this back to work. We would get that Q times change in V is therefore equal to negative work, right? So we talked about how change in U is the opposite of the work done by that force when we're changing systems. When we're changing systems. So negative Q times change in V is equal to the work, which is going to equal the integral from RA to RB of let's do Q times E, right? So for point charges, right, it is gonna, or dr also, by the way. For point charges, it would be KQ over R squared, but when we're not dealing with point charges, it's going to be whatever the electric field is as like a function of R. So if you think about cylinders, whatever you use Gauss's law for, right? There's all sorts of things. It's going to be that Q times E, the more general form of the electric force equation. So now, hey, these Q's can drop because the charge of whatever's going through the electric field, right? The thing that's moving, that's not going to change. Probably not. I hope not. That would be really weird. It's not going to change. So I can drop the Q's, and I get that the negative change in V is going to equal integral from RA to RB EDR. Simple as that. All right? That is the equation that relates voltage to the electric field. If you integrate the electric field across a certain distance, right? So let's say across this path, right? Across this path this charge takes, and let's say it's positive, so it will move away. Across that path, the electric field is going to change, and if you take the product of the electric field at that point times that tiny distance it moves, sum that all up, you get the total negative potential difference, right? So this quantity, if you take the electric field from RA to RB, this quantity is positive. So the change in V, the final voltage minus the initial voltage is negative because it's going from high to low potential. So negative times a negative quantity is how you get the positive thing. You can also, if you use your integral property, you can also switch the bounds. So change in V is going to be from RB to RA. You kind of like going backwards, I guess. So yeah, that actually makes sense. You're going backwards. If you go backwards and you integrate that, you get the actual potential difference. So that's how the voltage is related to the electric field. If you think about equal potential lines, right? So if I draw a positive Q and I create, let's say, a equal potential map. So these are circles that represent where is the potential the same, right? So at this point, the potential would be the same as this point, but it wouldn't be the same. So, or I should say, the potential around this loop is all the same. It's just not the same as this loop. So to get a potential difference, you would have to go from like this point to this point, right? Well, hey, guess what direction the electric field is? It's gonna be like that. It's perpendicular to the equipotential lines. Why does that make sense? Because of this goddamn equation. You can't get if a zero potential difference really means, ooh, this is interesting. Now it would mean, in a perfect world, it would mean like zero electric field. But if you think about it, you can get a loop, you can get a path like this, right? A circle just going back. So if you were to sum up the electric field at this point, this point, this point, and then if you were to start subtracting the electric field, because this is a dot product, so the angles would all work out so that you get, this is a dot product, I should have mentioned, because work is a dot product of the force and the displacement. But if you were to take this integral, it would end up being zero because the electric field would there be zero. So what you can't get an electric field that somehow curves like this. Because what that means is when you go along this path, the electric field integrated with respect to the distance you travel, hey, that's going to be that's going to be some positive or negative number. That should be a change in V, but we know from equipotential lines that's impossible. That's why electric field lines are always perpendicular to your equipotential line. So hopefully this kind of makes sense. Thank you for watching.